Hey guys, welcome to the what. So today we will see closed loop simulations of DC to DC buck converter, which is non-isolated, right? So we have seen the simulation of open loop buck converter in the earlier videos. I will leave the link to that videos in the description. So let's get started. So as we know that a buck converter is a device which will step down the input voltage, right? We already know its principles, its fundamentals, and how to design an open loop buck converter, right? So today we will see what extra steps we need to do to design a closed loop buck converter. So this is the main feedback circuit. So as we know, this is our input voltage. This is our main circuit. Here we will get some step down voltage, right? And this is the triggering circuit, which will trigger our semiconductor switch like MOSFET and IGBT, right? So now if we see, then all these things, these four things will make our open loop buck converter, right? We have already seen how to design an open loop buck converter in our earlier videos. Today we will design one extra thing that is known as a feedback loop, right? So what is this feedback? A feedback means we will take some value from the existing output voltage, and then we will give this value to our triggering circuit. So according to it, it will generate the gate pulses and it will give to the main circuit. And the cycle will go on and go on until our reference voltage has arrived, right? So a reference voltage means we need some reference which we will give to this triggering circuit. At what voltage do we need this buck converter to run on, right? So for example, if we are giving 100 volts as an input and we want that this buck converter should work on 50 volts only, so we'll write 50 volts here. And if in future, while the circuit is still going on, circuit is on, and if this input voltage will change from 100 to 80, then also the output will remain same. This is the main concept of closed loop converters, right? So let's see that what do we need to design this feedback loop. So these are the same components that we used earlier to design a buck converter. You can check that video out. And these are the controllers that we will need now to design our feedback loop, right? So a PID controller, which is the most important thing, one add block to compare with a reference, and one constant block to act as a reference, right? So let's see how to design it. So the circuit which you are seeing is the exact same circuit that we have designed in open loop buck converters. So please visit that video and make this circuit understand the principle, then come back here, right? So now we will design our feedback. So first we need PID controller, then we'll need add block, and then one constant, right? This one. Now let's arrange this. So we are giving a feedback, so it will point towards the backward side. So now what is this? What is the output of this PID controller? So output of the PID controller will range from 0 to 1, right? So we can say that indirectly we are controlling the percentage of duty cycle, right? We are using this particular constant here, we are changing the duty cycle from 0% to 100% duty cycle. It means right starting from 0, 0.1, 0.2 up till 0.9 or 0.99, that is the 99% duty cycle. We can't go till 100. We will understand that why we can't go till 100. So now what we need to do, we just need to replace this constant with the output of this PID controller, right? And to the input of this PID controller is the difference of our reference voltage and our input voltage, that is this. Let's change the signs. Right, so that's it. This will complete our feedback loop. So now let's see how this thing will work. So we have our input DC voltage as 100 volts, and we know that we can control this buck converter right from 0 volts to 100 volts. So on 50 volts, we can expect a 50% duty cycle, right? So let's put here 50, and we will run this till 1 second. Let's see what the output we are getting. So we can see here approximately we are getting 49.73, that is near about 50, right? So let's see the scope. So we can see the blue line is our constant DC input voltage and the yellow one is our voltage that we are getting, that is near about 50 volts, right? Now let's see the working of the PID controller, the waveform of the PID controller. Yes. Okay. It will, we have to change some values actually to tune our PID controller. We can use these same values as well, it doesn't matter, but here I have designed, or I have tuned this PID controller according to our design. So we will only use proportional and integral. We are not using a derivative here. So we will take only PI. For proportional, we will take 0.0001, and for integral, we will take 0.1. These are the designed values, right, according to this particular circuit. And we will see in further videos that how to tune or how to decide these values of a PID controller, right? Let's get started one more time. Now we can see that as it is coming exactly 50 volts here. See the output. It is way smoother than the last time's output, right? Then let's see the waveform of this thing. So as we can see here, the yellow one are our carrier signal, and this one is our main signal, which will be compared. So let's see that at what value it is being constant, right? So we can see here it is near about 0.506 or 0.507, right? See, so it is near about 0.5. So if we zoom in, then we will see that waveforms are of 50% duty cycle, right? So now we don't need to adjust the duty cycle now. Now we just need to give our reference here, and the controller will decide itself that what duty cycle it needs, right? So let's see, I want 75% or 75 volts as my output. So now we can see here we are getting almost 75, that is 74.99. Let's open this. We can see here that we are getting 75% duty cycle, right? So this is the design. So now what we will do, we will keep 75 only, but we will change the input DC voltage, that is up to 150 volts, right? So we are changing the input voltage. So let's run this. So then also we can see that if we change the input voltage, the output voltage will not change, because thanks to the PID controller and the feedback loop, right? So that means that we can fix a value according to our design, and we can see, then we know that output will not change, right? Now let's do one wonderful thing that I really like to do. We will run this whole circuit for 100 seconds, and we will not stop the circuit this time. We will change our reference voltage. We will change our reference voltage while the circuit is working, right? So when we use such type of connections in an electric vehicle, we are not switching off the engine each and every time we need a certain speed, right? Our motor is on, our circuit is already on while we change the accelerator. So according to it, our voltage which are reaching to the which are reaching from the batteries to the motors will change while our car or vehicle is running, right? So let's see that. So here let's keep 50%. This is no, not this one. Here let's keep 50 volts initially. The input DC initially is 100 volts. So let's run this. So now we can see here it is almost 50. It will move from 49.99 to 50.1. Let's see the output. So we can see here the blue one is our output that we are getting. The blue one is the input and the yellow one is the output that we are getting. Let's see the output of our PID controller. Right. See, PID controller will also work at 0.5, right? Now we will not stop the circuit. We will just change this reference. Let's change this reference to 25. So now we can see here our output voltage changed to 25 volts. Let's see the output. So what we are seeing here, we are seeing that the yellow one will drop down up to 25 volts, then it will remain constant. It doesn't matter what is the input. We are right now, we're not changing the inputs, right? So this function, we can use this function as an accelerator in a electric vehicle, right? So like at 25 volts, motor is running at 500 RPM. So like if you want to increase the speed, so we will just change this 25 to 50. So now the output will be of 50 volts and the motor will go accordingly, right? If we see the output of a PID controller, let's see. So now as we see, as we know that after changing, it came down up to 0.25, right? Now let's change this to, if I want higher speed, so I'll require a higher value of voltage, right? So I'll write 75 and apply. So now it will take some microseconds to adjust, but it will reach to 75 volts in no time, right? So let's see the output, that how, yes. So we can see that after, like, it will take a certain amount of time this time. So like it will take around 23.5 and 24. So around it will take 1 second, right, to tune itself. So this will completely depend on the value of, on the tuning of a PID controller, right? So this is the thing. Let's check the output of the PID controller as well. So here also we can see it will increase up to 75% duty cycle, right? Now let's say that input from a battery will change. So now this configuration will work in a solar plant where the input from the sun is constantly changing, but output, that if we are charging a battery using a solar panel, then the input to the solar panel will be a variable term, a variable number, because different times, like in 24 hours we will get on an average 8 hours of sunlight, and in that 8 hours as well we will not get constant sunlight. That means the input might vary, but the output to charge the battery should be constant, right? So for example, if the output to charge the battery is at 75 volts, right? So then if we change the input, let's say at morning 10 o'clock, we are getting the intensity of a sunlight equivalent to 100 volts of input. Now at in the afternoon at 2 o'clock or 3 o'clock, the intensity will increase, and now the intensity is equivalent to 150 volt input. But then also our output should not change, right? So see, I changed our input while the cycle is working, while the circuit is working to 150 volts. Then also our output is constant only, that is near about 75. But our PID controller will take some time to tune itself here as well. So let's see. So here we can see that the yellow one is the output. So while we change the input from 100 to 150, the blue line, the output changed a little bit. So we can see it changed a little bit, the yellow line, but then it came back to 75 volts, right? So this is due to the tuning of a PID controller, right? So now we are still getting the output of 75 with a higher input voltage of 150 volts. If we see the input of PID, yes. So according to it, PID will adjust to give us a higher duty cycle, right? So now let's say it is evening 6 o'clock and the amplitude will decrease to 90, near about 90. And let's say our battery, we only want 25 volts, right? And the input will change up to 80. So then according to it, at 80 volts, it will give us 25 volts that we require. If we see the scope, then in the scope, what we will see that while we changed our input from 150 to 80, our PID controller was unstable for a certain amount of time, but it was stable after a few microseconds, right? And it will constantly give us 25 volts as an output. Same thing we will observe here as well. So according to it, the PID controller will change its constant value, and according to it, our duty cycle will change, right? So this is the whole concept on closed loop control of a boost converter or closed loop circuit of a boost converter. But still, this is an non-isolated one. We will see in further videos how to design an isolated converter using this closed loop design, right? So if you have any doubts, if you have any questions, please do let me know in the comment section. I'll try to answer them all. And if you have any suggestions for my video, then also please do let me know. If possible, I'll make those changes, right? So I guess that's it from my side. Thank you so much. Bye.